G'day. In this video, we're going to be looking at a key concept which comes up through physics, which is very rooted and grounded in mathematics and numeracy, and that is rates of change. So when we're looking at a rate of change, we're looking at some sort of measurement that defines change in one variable versus another variable. So when we start talking about these terms, variables, this should be quite reminiscent of a lot of the skills and concepts that you would have covered in junior science. We know that we have an independent variable and we have a dependent variable. Independent being the one that within the scope of an experiment is chosen to be changed. The dependent variable is the measured result of that change. When we have a rate of change, we're looking at comparing those two variables and seeing how one changes the other. A lot of the time, the independent variable in a rate of change is going to be time itself. We usually express rates of change using per terminology, so it's always the dependent variable per independent variable. If we were to measure plant growth, we could measure the rate of change as centimeters per day, so the growth, the dependent variable, per the independent variable, which is time. If we were measuring the expansion of a wet sponge, then the dependent variable would be the volume that's changing, and that would be changed per mil of water added. The price of vegetables, the amount that we pay, the dollar price, is the dependent variable, and the amount paid depends on the number of kilos, so dollars per kilo. And last example here, flow rate of liquids, we could look at the amount or volume of water which is being released, say, from a tap every minute. Now, rates of change can be graphed. As always, we put our independent variable here on the bottom. In this case, our independent variable is time, and then our dependent variable always goes up on the y-axis. In this case, the dependent variable is our gold price. So effectively, we can see that there is change happening between the two variables, time progressing and the gold price changing. The rate of change is variable though over these years. The gold price doesn't just go up by the same amount every year. We can see fluctuation from year to year. At points, there are increases. At other points, there are decreases. We may see that there are some general trends, some general rates of change. We could determine that with a line of best fit, but this is quite a complicated graph and is a little bit difficult to explicitly see any pattern in the rate of change at any particular time. Flipping to something that's a little bit more simple, here in this example, we can see that temperature is something that is changing over a period of time. Again, independent on the x-axis, our time, dependent our y-axis. In this case, it's temperature. Now, in this example, the rate of change is consistent throughout. The temperature is increasing by a consistent amount as time progresses. We can actually calculate on this graph the rate of change. What is the rate of temperature change as time progresses by determining the gradient of this line. We should hopefully remember that gradient is equal to rise over run. In this case, rise is 140 minus 20 degrees, which comes to 120 degrees. That's the increase of temperature that we've seen over the graphed period of time. The run is the time that's progressed. We can determine that by doing 10 minus 0 seconds. That's 10 seconds in total. In other words, over the 10-second period of time, the object that's been measured has increased its temperature by 120 degrees. The gradient would be equal to 120 over 10, which is 12. In other words, the object sees a 12-degree increase every second, or 12 degrees Celsius per second. That is our rate of change. Something that's really important to acknowledge or discuss as well when we're looking at rate of change are the units of measurement. Now, we always calculate rate of change as dependent variable divided by independent variable, or rise over run. So there's an equivalence here to our gradient that we found in the graphical representations that we saw. As such, the units of measurement for the rates must match the form in which they're calculated. This is a concept that we will continue to build on, this idea that units of measurement need to match how something is calculated. But for now, what we just need to sort of acknowledge or understand is to calculate plant growth, we would take the amount of growth in centimeters, divide it by the number of days, and we'd get our rate for plant growth there. The units of measurement are then displayed as centimeters per day. For the expansion of the wet sponge, we can show the units of measurement as cubic centimeters per mil. For the price of vegetables, dollars per kilo. Flow rate of liquids, milliliters per minute. We can also use index notation, which you would have seen in previous videos as well. You should be aware of that notation as well. To make some connections to physics rates of change. So far, you've seen two measurements in particular, meters per second for velocity and meters per second squared for acceleration. In the example for velocity, what we are measuring is the amount of distance traveled per second. In the example for acceleration, the rate that's actually being shown is a little bit difficult to see when it's written like this. And we have talked before, we can sort of look at acceleration as the change in velocity over time. And a way that we could be writing that is something like meters per second per second. And the way that we can sort of see how those units sort of represented mathematically with an equation might be something like velocity divided by time. Hopefully this video has given you a little bit more of an inside look into measurements that are based on this concept of rates of change. And with this knowledge of how rates of change work, this might help to make a little bit more sense of how those rates are calculated, why they're calculated in the way that they are, how they can be displayed graphically, and also how units of measurement may be reflected in final responses.